Hi, and welcome back, AP kiddos, to our equilibrium chapter. Now, we're going to be covering equilibrium for quite a while. Currently, the AP test, the very first question on the free response is always some sort of equilibrium. Now, we're going to find that if we follow the same framework, it doesn't matter what sort of equilibrium it is. If you don't follow the framework, you're likely to get lost by the first few words. So let's take a look at the types of things we'll be covering. Now, there are effectively three different questions that we want to ask about reactions. One question is, will it go? And by that I mean, will it go spontaneously? That means without really any outside intervention other than maybe a kickstart on the activation energy. And that's going to be covered in our thermodynamics chapter. And that's going to come, probably towards the end of this 9 weeks. How far will it go? We've seen on and off throughout the semester, and you will continue to see through this unit and beyond. And that's stoichiometry. And stoichiometry reactions are assumed to go 100% to products. Now, there are many that go less than 100%, and that's where we're landing right now, is on equilibrium. And in actuality, we're ultimately going to be combining reactions that go 100% and then products from that which will jump into an equilibrium. And then last unit we covered how fast will it go, kinetics. Now, there is a relationship, or there are relationships between these. There's a fairly strong link between thermo and equilibrium. And there is a definite link between equilibrium and kinetics. Now, what you're going to see is that there's not a very strong link here, or at least not an obvious one-step link that we'll be exploring. And that's something that justification questions like to trip you up on. In the midst of a question about thermo, they'll start asking you how fast things go. And so we'll address that when we get to the thermo topic. Now, a state of equilibrium, when we say something is at a state of equilibrium, we're really referencing a closed system. In other words, there's no other source of reactants and products other than what was initially put in that closed vessel. So the only way to make product is to consume reactant, and the only way to make reactant is to consume product. Now we'll address some stresses to that closed system later, but for now we're assuming it's a closed system. Now we're looking at reactions that are reversible. In other words, as soon as quite a bit of reactant has collided with one another to make product starts undergoing collisions, and in the process of undergoing those collisions, more reactant is formed, and vice versa. And so both reactions will go until they reach a state of what we call equilibrium. And we want to study this, and the idea of percent completion would be helpful. For example, we saw that stoichiometry goes 100%. So why don't we talk about equilibria that goes, say, 52.3%? Well, that's not a bad way to look at it, but we're going to find that varying initial conditions can actually impact that percent. So since there's not really a constant we can study, that turns out to not be as helpful. And so we're going to talk about sort of marketing terms. We want to compare the relative amounts of products and reactants. So we want to look at how much money we can make, for instance, making our products. And as we're monitoring a process, we want to see that relative amount. So we're going to discuss this in terms of the reaction quotient, Q. Now, you need to know not just the symbol Q, but that term reaction quotient. So if you're keeping a to memorize list, I would certainly include that in your to memorize. So somehow we want to relate our products to our reactants. Now, certainly as scientists, we could have done it the other way around. But again, in terms of marketing, usually we want to make some product because we want to sell that product. We want to make either buckets of money or, we want to make a lot of money for altruistic reasons, to give it away, whatever is in your personal temperament there. And so we tend to look at, or it was decided to look at products over reactants in some form. Now, we're almost at that state of equilibrium, so hold that thought. When we look at that Q, we look at what's called a law of mass action. And what's lovely about this, we have products on top, notice, and then we do have reactants on bottom. And hopefully you've been able to pick up, it's a little hard to see here, but the powers that we get here, unlike kinetics, overall reactions in kinetics, the powers come right from our balancing coefficients. So we won't have to deal with the mechanisms and the derivations that we saw in our kinetics. We will get to treat an overall and use those coefficients directly. And notice that we use both products and reactants. Now we're going to be using brackets. Remember, the brackets stand for molarity. And you are also going to see partial pressures being used. So if you're given pressures, you have to use the partial pressure symbols. You can't use the bracket symbols. All right. Notice here that we're talking about multiplication and division, not addition and subtraction. Very common mistake. And we're going to find that we're not going to be including solids and pure liquids. Hopefully there's this little tug on your memory from pre-AP chemistry. Now, we are definitely looking at the Q right now, but Q is going to change with time. And that's not very helpful for us. I mean, it is going to be a helpful term, but in terms of having tables and defining reactions and studying reactions, Q is going to lead into our state of equilibrium. And our state of equilibrium occurs when the rate of our forward reaction equals the rate of our reverse reaction. Now, that may appear to be static, but it's not a static state. There is no apparent change. For example, if we were studying colors or conductivity or pH or some other property of the system, there would not be an apparent overall change in reactants and products, because every time, if we look here, these are our reactants here, right? Reactants get consumed over time. Products are formed over time. All right. And we reach this state where every time a product is formed from reactants, reactants end up being formed from products. So in kinetics term, our rate constant in the forward direction is equal to our rate constant in the reverse. So yes, it appears to be static, but that's only true on our macroscopic level. If we looked at the microscopic level, if we could tag atoms with, say, a radioactive isotope, some sort of tracer that we could trace what's going on in the process, what we're going to see is this continual movement back and forth where products form, reactants form products, products form reactants, reactants form products, products form reactants, but it's happening at the same rate. And what happens then is that ratio that we call Q becomes constant. So Q becomes K, the equilibrium constant. And they're set up the same way. It's still products on top, reactants in bottom. But instead of a variable value, we reach a state of a constant ratio between those two things. Now, in this picture, we're seeing more product than we are reactant. But that is specific for this reaction. There will be times in which reactant will be overall greater than product. There will be times when product will overall be greater than reactant. So there's no magic in where these two lines end up. So in this case, this would be what I would call the Q region over here, and this region here where the rates are equal would become our K, or equilibrium region. Now, Q, we're going to find, can also arise if something disturbs the equilibrium and alters our equilibrium. We would enter a, range of Q and get back to our K. So Q is bigger than this, but certainly Q references all ratios that are prior to reaching equilibrium. And we're going to talk a lot about initial states and Q. So Q is what we're going to typically be talking about when we reference initial states. And then K would be our final, or our equilibrium. Whoops, that's an L, our equilibrium states. So that gives you a brief introduction to that, and I'm going to go a little bit more into this in our second video when we get into a little bit more detail of that law of mass action, or our equilibrium constant expression. So until then, this is signing off, hoping you have a very Merry Christmas too.